Consider the following truth table. We have the atoms P and Q, and we have each possible way of assigning truth values to those atoms. In the rightmost column, I've written down the values true, false, 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 but I've left the very top of that column blank. What formula ought to go in that blank? That is, what formula is true when P and Q are both true and false on each other valuation? It's probably pretty easy to see that the formula P and Q fits there. What if we change the truth values in the last column to true, 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 false? What formula has this truth table? It's probably pretty easy to see that the formula P or Q fits this time. But what if we change the truth values in the last column to, say, false, true, true, false? What formula has that truth table? Can we even be sure that there is a PL formula that has this truth table? And even if there happens to be a formula that has this truth table, what if we construct another table? Will there, for any given truth table, always be a PL formula that we can construct that has that truth table? In fact, the answer is yes. I'll show how to do it for one truth table, and it should be pretty easy to see how that same method could be extended to any other truth table. So here we have the atoms P, Q, and R, as well as all 8 possible valuations of them. Let's suppose that in the rightmost column, we write down the value true in, say, rows 1, 3, and 7, and the value false in all the rest. Here's how we can construct a PL formula built out of the atoms P, Q, and R that has this truth table. First, we need to talk about what a basic conjunction of a set of formulas is. A basic conjunction of some formulas takes each of those formulas either as is or negated and conjoins them. For example, consider the atoms P, Q, and R. One basic conjunction of those formulas would be P and Q and R. In that case, I've just taken each of the formulas as is and conjoined them. Another basic conjunction of those formulas would be not P and not Q and not R. In that case, I've taken the negation of each of the formulas and conjoined them. Another example would be not P and Q and R. There I've taken the negation of the first, left the other two as is, and conjoined all of them. You might have noticed that, strictly speaking, the expressions I've just been writing down are missing a set of parentheses, because strictly speaking, each conjunction sign should come with its own pair of parentheses to clarify what formulas it's conjoining. However, even though we haven't pinned down with parentheses the scope of each conjunction sign, it doesn't matter in these cases, for regardless of how we do it, the meaning of the formula wouldn't change. For example, one way to pin things down with the last expression written above would be to say that the first conjunction sign is joining not P and Q, and then the second conjunction sign is joining the conjunction not P and Q with R. Alternatively, the second conjunction sign might be joining Q with R, while the first conjunction sign is joining not P with the conjunction Q and R. But either way, the formula is saying the same thing. Any way you slice it, so to speak, it's just asserting that not P, Q, and R are all true. So when writing out a basic conjunction of a set of formulas, we'll just leave out any internal bracketing that would officially be required. Okay, now back to our truth table where we have the atoms P, Q, and R and all 8 possible valuations of them. We want to construct a formula out of those atoms that's true in just rows 1, 3, and 7. The first step towards constructing that formula is to notice that for each possible valuation of the atoms P, Q, and R, there's a basic conjunction of those atoms that's true on just that valuation. For example, take row 3, where P is true, Q is false, and R is true. To get the basic conjunction of those atoms that's true on just that valuation, leave the atoms that are assigned true as is, so leave P and R as is, negate any atoms that are assigned false, so negate Q, and then conjoin the resulting formulas. That gives you a formula that's true in row 3, but false in all the other rows. To see why that formula is true in row 3, note that in row 3, P and R are both true, so the first and third conjuncts of P and not Q and R are both true in row 3. Moreover, Q is false in row 3, so not Q is true in that row. So the second conjunct is also true in row 3. So all the conjuncts of P and not Q and R are true in row 3, so that formula is true in row 3. To see that that formula is false in every other row, just note that in any other row, at least one of P, Q, and R must have a different truth value than it does in row 3. But if P or R has a different truth value, that would mean one of them is false. And if Q has a different truth value, that would make it true, which would mean that not Q is false. So on any other row, P and not Q and R will have at least one false conjunct, and so it will be false. So far, we have the basic conjunction of P, Q, and R that's true just in row 3. Now we construct the basic conjunction of those atoms that's true just in row 1, and the basic conjunction of those atoms that's true just in row 7 via the same procedure. So in row 1, P, Q, and R are all assigned true, so we leave each of those atoms as is and then conjoin them, giving us P and Q and R. In row 7, P is false, Q is false, and R is true, so we negate P, negate Q, we leave R as is, and then we conjoin them, giving us not P and not Q and R. Now, ultimately, we want a formula that's true in rows 1, 3, and 7, and false everywhere else. So the last step in constructing that formula is to take our 3 basic conjunctions and disjoin them. The resulting formula will be true in row 1 because its first disjunct is true there. It will be true in row 3 because its second disjunct is true there, and it will be true in row 7 because its third disjunct is true there. It will be false in all the other rows because in the remaining rows, all of its disjuncts are false. So now we have a formula that fits the truth table we wrote out. What if we change the truth table? For example, what if we want a formula that's true in rows 2, 4, 5, and 6, and false everywhere else? We can use the same overall method. For each row where we want the formula to come out true, we construct a basic conjunction that's true in just that row, and then we disjoin all of those basic conjunctions. Easy as that. That method will not always give us the simplest formula that does the job. It'll always give us a formula that has the truth table we're looking for. The only case we haven't covered is the case where I want a formula that comes out false on every row. If I want to build a formula out of the atoms P, Q, and R that's false on every valuation of those atoms, one way to do it is to take the conjunction of each atom in its negation. So that would give me P and not P, Q and not Q, R and not R, and then disjoin those conjunctions. Each disjunct will be false in every row, and so the whole disjunction will be false in every row.